In this screencast, we're going to look at what's called the fundamental theorem of line integrals, the easy way to find work. It basically goes back to first semester calculus and looks at the fundamental theorem of calculus, which you may remember as a to b, f dx is you find an antiderivative, and then you plug in b, you plug in a, and you subtract. Does that sound familiar? You plug in b, you plug in a, and you subtract. Well, what that means is if you take a function and you have its derivative, then really, if you want to integrate a derivative, you just take the function you started with and you plug in the two endpoints. That's our fundamental theorem of calculus. Well, it turns into a different formula in high dimensions. If you've got a vector field that has a potential and you're going to calculate this integral, so if you're going to integrate the derivative of some function, dr, along some curve, then the idea is all I have to do is integrate the function. So integrate big F to get its potential, and then plug in the endpoints. So if you've got some curve, and it's traveling through space, and you start at point A, and you end at point B, and you know that the vector field you're working with is conservative, or the vector field has a potential, then all you have to do is evaluate the potential at the endpoints. So take f of b minus f of a, and you're done. So let me give you an example, and then we'll actually explain why it works. So if you take a vector field such as x plus 2y and 2x minus 4y, does this vector field have a potential? A simple way to answer that, I take the derivative. If I take the derivative with respect to x, I get a 1 and a 2. If I take the derivative with respect to y, I get a 2 and a negative 4. Those numbers are the same, so a potential exists. I can find the potential by integrating. I get an x squared over 2 plus 2xy when I integrate this with respect to x. Now I integrate here with respect to y, which gets me a 2xy minus 2y squared. The 2xy has both an x and a y in it, so it should appear in both spots, and our potential is sum the terms x squared over 2 plus 2xy minus 2y squared. This is our potential. So if I want to find work, suppose I want to find work, and I'm going to start at, we need a point. So suppose we start at the point 3, 0, and we end at 0, 2. And we follow some path. We end here. We could go along a straight path, we could go along some funky path, we could spiral around a few times, and then in there. But if we start at this point and end at this point, then we can start at 3, 0 and end at 0, 2, and I could find the work done, or you may see it written as 3, 0, 2, 0, 2, where we have an x plus 2y dx plus 2x minus 4y dy. Does that look like an m dy? X plus an n dy. Here's your m, here's your n. Just put them in. That's work. Well, the fundamental theorem of calculus, or of line integrals, says I can do that by just taking the potential, which I found, x squared over 2 plus 2xy minus 2y squared. And I just have to plug in the points. 0, 2 would be the end point. 3, 0 would be the start point. Well, let's just plug 0, 2 in. If you plug in 0, you get 0 plus 0 minus plug in 2. That's what happens when I put 0, 2 in. Now I've got to subtract what happens when I put 3, 0 in. So that would be 9 halves plus 0 minus 0, which means it's minus 8 minus 9 halves. That's it. Did we have to parameterize a curve? Did we have to do any of the parts involved with parameterization? No, not at all. Find a potential, plug in the endpoints. That's it. So the idea, why does it work? Well, if you go back to first semester calculus, the whole idea is if you take f of b minus f of a, that's really integrating little changes in the function. It's adding up. This is a difference in the function. You can add up little differences in the function. Pictorially, that means I've got some function from a to b, and I'm looking at the total difference in the function. Well, if I found the little differences, and I call that df, and I add all those up, I should get the total difference. Well, this is the same thing as doing a df dx times a dx, which really means you're adding up f prime dx. That's essentially a proof of the fundamental theorem of calculus. We're now going to jump it over into a different realm. What if I take df dt dt, and I change the variable from an x to a t? Well, if I think of this as a function in high dimension, since t is a time parameterizing a curve, then this is really f prime times r prime dt. The chain rule, I can think of this as a df time, or a derivative of an f times the derivative of r. It's just the chain rule, and I'm adding those up. Well, the derivative of f is our gradient, and r prime is our r prime, which is this dr, so this r prime dt is really our dr with a vector above it. And that's essentially the reason it works. It's the same theorem, we're just changing the x to a t and using the chain rule to get that product. That completes this week.